So, who we are. This is Matt Smith sitting down here in the front corner. He's a VPP committer. He's a primary architect for our Tensor product and one of the co-developers on LinuxCp, which is what we're here to talk about today. I co-own the company, and we're nice clothes and go out and talk to customers and investors, and I like coffee and talking to people. In fact, when the barista asks me how I like my coffee, how I take my coffee, I say very seriously. So, just to set some context, because even here I've heard some things where people intermix terms about control planes and management planes. So, a data plane is basically a set of functions and processes that provide, packet transformation. Get packets from one interface to another, do some rewriting along the way. Often implemented ASICs. There's a lot of switch ASIC stuff here this week or these 2 days. VPP is pure software. Just runs on a commodity x86 or ARM platform. Control planes are functions and processes that basically determine what path to take through the data plane. Examples of these are routing protocols like OSPF or BGP, spanning tree protocols so you don't end up with loops in your network, link distribution protocols, which is MPLS, which that's the last time I mentioned that in my talk, and even things like IKE to determine what the security associations are can be thought of as control plane protocol. And then a management plane is all the things you do to basically control and monitor devices. SNMP is a classic example, but so are CLIs. So your operators want to be able to type things like, show me the route that this packet would take according to your table. So you put it all together. I stole this picture off of Wikipedia because that's where you steal pictures these days. There's actually 3 routers here, but the middle one shows where all the pieces conceptually fit together. So you've got your management plane with a CLI or a configuration API, something like netconf maybe, control plane in the middle, doing a lot of processing of things like routing protocols to program the data plane to do the right thing. So how many in here have heard of VPP? Great. Half of you. For the other half of you, VPP is a very high performance packet processing stack. It runs on, like I said, on commodity CPUs. Get your Intel CPU from C2000s up. It's been part of products from Cisco and apparently ZTE since 2006 or so 15 years of production deployment. Cisco open sourced it in 2016 under an Apache 2 license, which means that even though there were patents on it, you have a license. And then LFN took that project over in 2018, and that's who this conference is for. So, real top level, L3 forwarding is 19 million packets a second on a little tiny Xeon D. You can buy faster processors. If there's anybody non-technical in the audience, 19 million packets a second is good enough for 15 gigabits at the smallest possible packet sizes, and if you go to 1500s, it's almost 250 gigabits. Now, if you're in telco, you care about small packet sizes, but if you talk to anybody in the security space, firewalls, that kind of thing, they always want to talk about big packets for some reason, bigger numbers, I don't know. It's been tested beyond a terabit per second, and you can see, 8 cores will get you there, even on a Xeon D, and 8-core Xeon Ds are a couple $100. About 14 microseconds of latency. So that's more than an ASIC, but that's like the one tax you pay here. The FIB is pretty scalable. It'll support millions of entries. It's got fairly fast convergence times compared to, say, the Linux routing table. Typically, the use is to use DPDK for the NIC drivers for the I/O in and out of the system. But DPDK isn't used anywhere else in VPP. It can take advantage of specialized instructions you have on the platform like AVX, AVX2, Neon on ARM. And then the way it gets fast is it employs, batching and you don't really have any context switches or mode switching like you do in a kernel setup. So it also can scale with multiple cores. It's architected such that it can just scale out if you have the orthogonality in your traffic. So it uses RSS to place the data on different cores or different queues for different cores. So overall, it's a directed graph of forwarding nodes, which is, 3 $5 words to basically say that it's got a different architecture than what you typically see in software systems. It implements a ton of network processing features. There's a full MPLS stack. There's an IPsec stack. WireGuard is a recent addition. All the tunneling protocols you can think of, IP, GRE, IPsec, et cetera, they're all handled. L3 forwarding isn't enabled for V6 and V4. There's a variety of optimizations it uses to get this fast. A lot of prefetching, and we'll cover why that works in VPP, but not so well in kernel networking. If you like, there's also a lot of gain to be had because it's very favorable in terms of how the instruction and data caches are handled, or what the artifacts are of using them versus kernel networking. And again, this is all portable C code. There's no special purpose code in the core of VPP. So if you can read and write C, or if you have developers who can read and write C, you're set. So scalar packet processing is, typical kernel networking, BSD, Linux kernels, they've all been the same. You have an interrupt service routine, takes a packet off of a ring that, the NIC has put it there. You basically process the packet by running a set of functions. Function A calls function B, calls function C, calls function D. You're making decisions in the middle of some of these functions to go a different way, but you still have this long call chain of functions. And then when you're done, you return from all of it eventually, right? And then, for every packet, you basically either drop it, punt it to the OS because the OS needs to see it for one reason or the other. Say it's even like an SSH session or a ping that's going to the local box, or you rewrite and forward. So this is very simple, but it presents some problems when you start trying to go at speed. When that call path length increases, you start spilling instructions that you'd already had in the iCache out of the iCache because the new functions need the iCache space. And so you end up thrashing the cache for every set of every packet that goes through. The only real solution to this is to buy bigger caches, buy a processor with larger caches or larger processors. That deep call stack also means that you start evicting locals to the functions from the data cache. And so they have to be re-brought in when you return into that function to start trying to do some processing inside that individual function. And then it's really difficult packet at a time to prefetch the data you're going to need for things like table reads, ARP tables, routing tables, other things that have basically stored a set of NAT translation tables, sort of set of information you might want to consult in order to make the decision about what you're about to do. So vector packet processing works a little differently. It takes 1 to 256 packets off the ring at once, and it forms a vector or an array. Or anybody here use Lisp in their life? Nobody. 1, 2, 3, 4. Okay. You basically get this list or vector of packets, and then that set of nodes are applied to that vector of packets one at a time. So it's much more like a Lisp map, idea, or if you're a Python programmer, apply. So it processes, one set of packets through each function at a time. So the packets don't so much move through the graph as the graph gets applied to the packet in place. So the first packet basically warms up the iCache. So the instructions are brought in from memory for that function if they're not already present, or out of L3 cache. They're cracked inside the microprocessor. These modern microprocessors, you have this big function that turns into little micro-ops. And those are cached somewhere else inside the CPU. So all that work is basically done on the first packet. And the second packet comes for free. It doesn't have to fetch anything. And the subsequent packets are the same way. This reduces the iCache miss, stalls you the iCache misses by about 100x. So 1% of what you had. And then if you have a set of packets, you can do things like fetch what you're going to need for the second packet while you're processing the first one and get that read from memory starting to come. In modern CPU systems, memory is 70, 72 nanoseconds away. And that doesn't sound like much, but if you're going to process even 10 gig of packets at line rate, at 14 million packets per second, you have 62 nanoseconds to get everything done for the next packet. If memory is 70 nanoseconds away, you're lost. You can't even do 10 gig at line rate. So VPP is this very fast software ASIC, right? If you don't like the way it works, you can change it. Try that with an ASIC. Go to your vendor and say, hey, look, we really want to do NAT a little differently. But networks require a bunch more than just a fast data plane. So you want to typically do routing and maybe some other things like DNS or even SNMP on the system. And VPP doesn't know how to talk to any of these. So you can start to try to construct these things inside of VPP, but we already have Linux. So LinuxCp, Linux control plane. And LinuxCp is a VPP plugin. It runs in the context of VPP and it has access to the insides of VPP as it needs to. But it basically mirrors these DPDK or VPP interfaces with a tap interface that appears to the Linux kernel. So every VPP interface can have a match, doesn't have to, but typically does, and can have a matching tap interface. So the kernel sees a bunch of tap interfaces and it knows what those are.
So these are for the locally originated packets, right?
Locally originated or packets that have to be delivered to the host. Right, so it's basically for punts.
Because you talked about, that's what I was looking at. Initially you were saying for the incoming packets, whether it would drop, punt to the OS, or forward, redirect forward. But for the locally originated, this is the method that we use.
Right. So, all packets received on a given VPP interface that are going to be punted, just like you said, not dropped or forwarded, get transmitted down the tap interface to the kernel. And the kernel delivers them just like they were received on one of its interfaces. This includes things like ARP. So, SML2 stuff also has to be processed to make the whole thing hang together. On transmit, any packets are received by VPP on the TUN interface or the tap interface are cross-connected to the VPP interface. So it's like an L2 cross-connect there. And then there's a separate plugin called LinuxNL, and it's a separate plugin because of history and politics that listens to Netlink messages, so we can synchronize the configuration of the paired interfaces when it comes from the Linux side, as well as route propagation. So in the internals of this thing are basically in the debug CLI, you type VPP control, LCP create, the VPP interface name, host IF, the tap name you want, and then you can put it in a network namespace if you want. It's optional. If you're using the API, it's a simple API message.
Do we have the measurement of how fast we can generate locally originated packets?
Yeah. You want PPS or you want full on rate?
PPS for, if I'm doing a software traffic generator,
Right.
right?
I don't know if I tried that. We tried T-Rex against? Yeah.
I just tried that for
Yeah. So. Anyway, LinuxCp creates the tap interface for us. You can think of this again as a pipe between the Linux kernel and VPP. VPP's backend code then basically leverages the vhost net infrastructure. So rather than have a set of taps, and taps are typically very slow, this leverages all this special purpose stuff that's in the Linux kernel to support KVM, or QEMU technically. And that means that it's much faster than taps typically are. There was a previous instantiation of this thing called the router plugin that used taps, and it was slow. So there's an option to create a TUN interface instead of a tap interface. TUN interfaces are L3, like a tunnel like the name implies. Tap interfaces are L2. On creation, a couple things happen. For tap interfaces, the MAC address of the tap is set to match the MAC address of the VPP interface, and the physical link state and speed are also copied over. So the taps look, for all intents and purposes, like real physical interfaces to the Linux kernel and to anything that knows how to inquire as to what the admin state is, or the link state is, or the MAC address is, all the rest of it, right? So Linux, it looks like everything's normal. And then for tap and ton, we copy across the MTU and the admin state. You can run, VLAN sub-interfaces with the one proviso that you have to have the pair already existing. So you have to have the base interface there before you can start creating Q and Q or 1Q interfaces. And then there's a set of callbacks registered so we can make sure that any interface state that gets set on the Linux side gets copied into VPP. There's a couple special mechanisms here to make this all work right. The first is that, again, the sort of local packets, things that match any interface address, automatically come up to the kernel. So if it's received in VPP and it matches an interface address early on, we forward it down the tap to the kernel. Inbound ARP packets they're processed by VPP, and then the result is copied back to Linux. So Linux also has an ARP table. So if you run ping from Linux, it just works. Right? Output packets coming across the tap interfaces basically bypass any routing lookup. They just get copied to the output interface on VPP, although you can run output functions in VPP against those, so things like NAT or ACLs can work. And then outbound ARP packets that come from the kernel are passed directly to the outbound interface. And then other either types are currently not implemented, but they can be. There's a place to put this. So if you have some other ether type you really need to process, you can put it in. Yeah, you can't just say, you have to implement some code to make that happen, but it's really not too hard. So the result is you have this fast data plane running on Linux and the Linux kernel basically in the same system, all but cooperating together. The one doesn't really know the other one exists except in this plugin. So the result is that VPP has its own internal DHCP client. We use the Linux DHCP client that you all know and love. It just works. I hate to sound like an Apple commercial up here, but the result of this is it just works like you expect it to. Or as somebody said yesterday in the Dent thing, it's just a Linux box, right? We use ISC's DHCP server. It just works. It doesn't know any different. SNMP works, but you have to teach SNMP how to read VPP's interface table, and that's about 100 lines of Python as a low-level implementation. It's really not that much code to do. NTP servers work, and of course, there's one thing I'm missing here. Anyone? Where's the routing? Right. So Linux NL is a separate plugin. It basically knows how to read and send Netlink messages. So as the Linux kernel generates Netlink messages, either because interface things have changed or because there are routes or other purposes, those get copied into VPP and the right thing happens as a result. So anytime something has an interface on Linux, you typically get a Netlink message, and we know how to process all of those in LinuxCp, or in Linux NL rather. And so the net of this is, sorry, that wasn't meant to be a pun. You can even use IP Route 2 to configure this. So tools that you already know from Linux can configure large parts of VPP. And, huh?
Does it also take care of discovering the IPsec essays and synchronizing it?
We actually have a plugin for Strong Swan. So you'd have to pick which one you want to do there, but you typically probably could process the Netlink messages for that as well and do the right thing.
Strong Swan can create essays in next level plugin.
Yeah, we didn't do it that part that way, but other people have. There's actually a plugin out in the world that works that way. Yeah?
What he's asking about is, can you set up the essays in the kernel SADB,
Right.
and have that propagate into the VPP, and then with that in the past, and there were challenges that I hit. So what we did was just create a plugin for Strong Swan that knows how to talk to VPP's shared memory API, and it installs them directly to VPP. It doesn't use this channel.
I guess technically it's possible to make that work, but it just hasn't been implemented. So you'd have to map all of that onto VPP's ACL infrastructure, and those two are actually different. And some of those impedance mismatch things are where you start to end up in, writing a lot more code. So anyway, if you run Bird on top of this, or FRR, or Quagga, or whatever, any routes it injects in the Linux kernel get copied into, including, fib support. So get copied into VPP. There's no policy-based routing in this, and again, you're going to run into differences in implementation. So this isn't a re-implementation of Linux kernel networking at speed. It's matching up, parts of what you need for a control plane on top of Linux into VPP. So, short example of how you set this up. The first couple commands are basically housekeeping, IPnet nsexec in the data plane namespace bash, right? Give me a shell going in the data plane namespace. System control restart VPP service, just make sure VPP is running. VPP control set interface MTU 1500, that's just housekeeping because it at least used to be, I think it is still is, that VPP interfaces come up with a 9,000 byte MTU. And if you're going to talk on the internet, you're not going to get very far with a 9,000 byte MTU. These two commands here, these two VPP control commands here are the only two VPP commands in this whole thing, right? The rest, the next command is really what I sort of showed on the previous slide. Basically create a host AI called VPP1 in the data plane netNS off of this VPP interface, right here. The next command is, just IP list, and there's only one interface running. Well, why, right? If you do IP list all, you'll see that the VPP1 interface isn't up yet because they don't come up by default. So if you configure the VPP interface, the tap interface up, the VPP interface also comes up, and then there's a couple commands here to basically show how to put a VLAN tag on top if you want. And the result is, at the end of this, you can actually run ping, assuming that you use real IP addresses and there's something on the other side of your default router that will answer.
Is there a corresponding network interface to the VPP?
No.
So there is no representation of an interface inside a kernel.
Right. So, and again, I sort of talked about some of those impedance mismatches you're going to have between what Linux kernel networking is and VPP. So one of the first things we ran into is that, VPP is a lot less strict about what it will accept as a route in the fib than Linux is. So in Linux, you have to have a matching interface that covers the next hop that you're about to set, and VPP doesn't care. It'll let you set whatever you want. The next thing is the kernel automatically removes routes when an interface is taken down. With V4, you get no Netlink messages about this. V6, you do. So we just take care of that so that before we take an interface down, we actually delete all the routes so things stay in sync. VPP fib, special route types, drop routes, that kind of thing, are very different than they are in VPP, so I don't think we even implement those.
We implement them, but in VPP you can have different paths that are part of the same route using one of those types, special types like drop or unreachable. And in the Linux kernel, that if you make a drop route or a black hole route, it has to be separate routes, a different type. You can't have that in one path, so that you have two paths and balance between them. If the first one's not up, you send an unreachable.
Yeah.
You can't, the model doesn't map correctly from Linux into VPP. That's kind of a superset.
And then Netlink sockets can be closed or overflow. And so we've added a lot of code lately to deal with overflows. And you can't just, set the buffer infinitely big because there are situations out there that will overflow your buffer anyway. We tried that. Performance flows between VPP and the host run at about 10 gigabits. And this is per interface. So assuming you have enough CPU, you can flow 10 gig over all of them into the host. Now, in VPP, it's a lot faster than that. And this is typically only used for control plane protocols or getting an SSH session to the command line or something like that. So this seems like plenty. If you can fill a 10 gig interface with anything other than, BGP updates, then I want to know what you're doing. This is a huge improvement over the old router plugin that used to be because it ran at less than a gigabit. And if you're trying to get, bring up a BGP session out of a cold start, it can take a lot of time to get the routes over a less than 1 gig path. And then router insertion and convergence to the fib runs at well over 100,000 routes a second, which there's no special purpose route processor here. This is all C code, and most of that time is dominated now by getting messages, Netlink messages, the routes into the kernel, and then getting the Netlink messages out and processed via this path in VPP. So you can think of it as almost 2 copies. And I'd like this to be a lot higher, but this is the reality of dealing with the Linux kernel for dealing with these first. And that is it, unless you want questions.
You mentioned the Thompson, you have a plugin to establish essays in VPP. Wondering whether VPP supports route-based VPP. Like in the kernel, one can have VTI interfaces or XFR interfaces for route-based VPP. You have that in VPP also.
VPP has that by creating, you can't, like we already discussed, you can't set that up in the kernel currently and have that propagate into VPP, but VPP has a policy-based implementation of IPsec, and it also has a routed implementation. So you create a tunnel interface and then just point the route to it, and packets get on there. People seem to like that better than the policy-based thing because people know to look at a route table the right way. And people who aren't used to, don't know that there's a tunnel running on the router or aren't used to troubleshooting that, don't know to go to the extra command to see the SA database, the policy database to find out, oh, this packet that I don't know where it's going, it got handled by this other thing on the side. The only thing our product supports is the routing. We don't try to use the policy-based.
You have a question? Go ahead. Which kind of interfaces you can use into a kernel? For instance, you mentioned hardware interfaces. Does it mean that this will have a valid PCI interface, or can you also mirror virtual interfaces?
You can mirror like IP tunnel interfaces or GRE tunnel interfaces, and they get set up as the tap driver has a tap, which is like emulates Ethernet. If you're using one of these L3 interface types, it uses a TUN interface, which is emulating just a point-to-point kind of interface. So there's no MAC address on the TUN interface, just like there's no MAC address on your GRE interface or whatever. You can emulate virtual interfaces. You can emulate, and we do, you can tie the loop back to the host system.
For testing purposes, for instance, can you do that?
Yeah.
Okay. Thanks.
We do that just because a lot of people, they're used to configuring on a Cisco router, the BGP endpoint is an address on the loopback interface. So to keep, a configuration like that in sync with what's, you're running BGP on the kernel, you just create a create a task for the loopback, and that ends up having to be routed once it reaches VPP. If you were using just the hardware interface, that kind of skips the routing hookup. But you can use a loopback interface, and that's just, you end up having to do a routing hookup once the packet gets into VPP.
So, as you mentioned, this defines a VPP essentially defines a software ASIC, right?
Right.
And so it means that it has a, defines some sort of forwarding pipeline. Right? So I don't know whether this question is, pertains to this particular topic here, but has there been any P4, model for this pipeline defined?
There is I think it's the project in Mana now. There was a project to basically bring P4 into a set of nodes, so you could run, P4 language things in that set of nodes and do packet processing there. It's never been, committed into the main tree, but there is a project on Garrett.
What is it called?
I'll look it up for you after this and find it for you.
Sure, I'll probably send you a link request.
Okay.
So you can connect on that.
Great.
Talk about this implementation of VPP over the next week or decade. Is this expected to PFsense?
Yeah, so I didn't really, I tried not to talk about our products. So many times you come to these things and all the vendors talk about their products, right? So we're mainly known for a thing called PFsense. And PFsense is a firewall, if you will, with a GUI that runs on top of FreeBSD. And so it's all kernel networking. It looks very possible to even bring this to FreeBSD, and there are internal efforts to bring VPP in a fully functional way to FreeBSD, so we could do a future version of PFsense based on this.
Thank you for that. I appreciate your comments.
Yeah.
But there is effort, you look at Kubernetes, right? Kubernetes has got two kinds of namespace processing, which does non-virtual switching and IP table processing, IPVS processing, and IPsec, which you already answered. So using this Linux and Linux kernel settings, is it possible to offload Linux root network namespace processing to based on this one?
Yeah, in fact, there was just recently a project at the last IETF meeting, which I might have just ended, or maybe it was in October, to leverage VPP instead of OVS DBDK. And they got some really interesting results for VPP. I won't ruin it for you, but if you want, I'll find the slide deck and send it to you.
I know that you answered that once the VPP interface is synchronized with the Linux kernel, and if you create any VLAN interfaces in the Linux, it automatically reflects the VPP.
Right.
Is it true with kernel interfaces like here, when you use IP kernel adds to create here interface? Does it reflect into VPP using this plugin type?
It might if you had an L2 kernel interface, like VXLAN or L2 GRE. We haven't tested it, so I can't really tell you for sure.
With GRE, you did not test, but L2 VXLAN
I haven't tested on VXLAN either. We support VXLAN, but I haven't tried it.
But we haven't tried plugging into this.
It gets created as a tab interface. I don't think that we've seen much of a use case, many requests to tie the VXLAN interface to the kernel. Because normally people are trying to run services on the kernel with the VXLAN interface. A lot of the use cases I hear about are bridging to some other interface. You don't really need the package to be handled all by the kernel, or a service running on the host system.
Yeah. So this isn't like a completely new way to configure VPP. A lot of it works. And in fact, a big reason why the Netlink plugin is separate is because the VPP maintainers argued against a new API. And so for the longest, I mean, they're basically part of the same thing now, but that plugin, that Linux NL plugin was maintained separately because, you know, we knew we wanted it, but we didn't think it was upstreamable for the longest time. And then there's actually 6 slides after the last slide here where I detail a little bit of the history of what happened here, and you can sort of dig into that and look and see that, you know, we architected it this way just so we could get the main body of it into the mainland of VPP, because we were told at the time that they would never take a second API to configure it, and that's actually part of their concern. At the end of the day, we'd been running it for, you know, over a year in our product, and they just decided they would just come in. But I don't think this, they want to maintain the API they have to configure all these features.
Do you have down the roadmap for Infiniband Driver cuts?
We don't have any plans around that, but I mean, I guess, you know, it's very possible that you could take an InfiniBand path that, you know, probably wanted to pass, you know, IP or Ethernet over that and make it happen. It's just C code at the end of the day.
Well, a lot of what we had people interested was L3 configuration, L3 forwarding.
Yeah.
So people ask about more specialized things, and all of them are possible. It's just, you know, there has to be enough interest shown that it seems like it's going to get used, that someone will go work on it. If we have customers interested in it, we'll go work on it. There are other people that are trying this to use it for different purposes. This is a topic that on the VPP developer mailing list, a lot of the questions that come up recently have been about, can I do this plugin? How do I use this and run into this problem? There seems to be a lot of interest by people because it gives them a way to run the applications they already have without having to know any internals of VPP or use different API than the socket API. So the possibilities of what you can do are pretty much endless, and it's just figuring out, does someone really need this? And for us, are they going to pay for it?
Is there something in the product kind of thing?
So for anyone who is doing a VNF, that could be a natural choice for them to
Sure.
do the VPP.
Yeah, because a lot of the configuration that you already have for the VNF probably already works.
Right.
And the pieces that don't are probably fairly simple to implement.
Sure. So it doesn't, I mean, VNF, now I'm going to use another example, CNF, right? Container.
Yep.
So that would be also the same thing. Like if I'm doing a CNF, now my network function is running in a container.
Right.
Would that be also the same thing if I use the VPP, or would there be something else that I would be looking at?
You could use VPP if that's what you want for your network function.
Right.
And again, a lot of the control plane or the management plane stuff probably already works. There may be small pieces you'd have to implement, but at least you have a framework to start with, if nothing else.
So today people use VPP and MT.io interchangeably, right?
Yeah, well, I mean, VPP was the name of the technology, if you will, inside of Cisco. FIDO got invented when Cisco decided to open source VPP as a covering organization, because there's a lot more you have to have than just a source code repo. Right? There has to be, you know, somebody there to interface to the world, and some place to hold documentation and that kind of thing. And then FIDO got absorbed into LNF 2 years later.
When people talk about FIDO, a lot of times they're talking mostly about there's other projects that are under the umbrella of FIDO. One of them is CSIP, which I created primarily for testing and benchmarking. And another one, which the guy that just left was involved with, is HICN, which I'm not sure what that does, but it provides some service using VPP. And there have been a handful of others. The been some attempts at RESTconf and NetConf support.
There's a thing called Open Daylight that, you know, and I think T-Rex was in for a while, but then it got taken back out.
So if I'm starting today to go to VPP, I would start with Fido.
I would start with Fido, yeah, because that's where the Garrett is and that kind of thing. So.
That's like a chance for performance comparative analysis with VPP Path and XDB.
We haven't done them because we don't do XDP in our product, but other people have, and you know, XDP at the end of the day is still packet at a time. It's an accelerated path out of the kernel, right? And so all of those things that VPP brings you in terms of the graph processing, you'd have to rewrite them. Now there is a XDP interface type for VPP, so you can make VPP run over XDP interfaces.
The thing I'm asking because I know Intel has published the chipset with XDP support on hardware.
Right. So then the question is, you know, what's your application that's going to run over that, right?
So
Could-
does VPP run on DPDK or top of it, or how does it?
So the interface, the only parts of DPDK that are, so DPDK is a huge set of libraries, and some of the libraries are actually POMO drivers. And so the POMO drivers get used for VPP, and the POMO drivers for basically for the interfaces and for the crypto offload drivers, like Quick Assist. And that's the only parts of DPDK that are in VPP. There's a lot of other things, you know, different libraries to implement things like, you know, fast lookup of routes that aren't in VPP.
Essentially, by using DPDK, you are bypassing kernel.
Right. But it's not the only way. I mean, there are some native interface drivers for VPP that do the same thing.
Our products mostly use the DPDK driver. They exclusively use the DPDK drivers, but a lot of people use some of the native drivers that VPP has developed native drivers for RDMA, which is basically Intel Linux mix.
And
Intel virtual function. Intel has an ABF driver. There's a native version of it in VPP. And there's a native Verdido driver, which the TAC uses the back, you know, some of the supporting infrastructure for that. And there's also native VMXNet 3.
But these are all user space drivers.
right.
Yeah. They're all user space drivers. You have the choice of you can use the DPDK version or these native versions. And there's some overhead. VPP has its own model of packet buffer and the metadata that gets passed through with that. And there's some overhead taking the buffer that comes from a DPDK homewood driver and populating that into VPP's native modeling buffer. So a lot of the developers at Cisco who worked on the native drivers, they recommend those to people to get higher performance. But I'm not sure exactly what the difference is between using one or the other. DPDK supports a whole lot of device types. If you want to use one of the native ones that VPP has support for, they're all user space drivers. It's all VFIO or UIO.
I mean, there is AF packet. So there are a couple ways to basically take packets from the kernel as well. There's AF packet, there's the XDB driver. If your NIC driver supports XDP, yeah. But like there's no XDP support for, you know, some of Intel's 10 gig NICs. So there's a more complete coverage still with DPDK than XDP.
Is this LinuxCp already part of the Linux distribution?
It's part of the VPP distribution.
It's part of it.
Yeah. So it's just a plugin in VPP, and it got it.
You guys have developed LinuxCp?
Yeah. Well, it's again there's like I said 6 slides of history there if you want to really go dig into it. But it started out that a guy that used to be at Cisco named Neil Rands had started a version of this. And then we started talking to various people at Intel initially, and then Cisco, about replacing the old router plugin. And Neil came forward with this sort of, I've been working on this thing. And then, from there, basically, we picked it up, and Matt, fixed a lot of stuff that didn't work yet. Another guy on the team named John Lolliger wrote the API component for it, so you didn't have to configure it via the startup commands. And then there are other people in the community who have fixed bugs and that kind of thing.
And how is it related to NF, Linux and CP, LinuxCp with Linux and
Oh, again, the Netlink driver was, again, kept separate because we were told by the VPP developers for the longest time that they didn't want another API. And I think they had some, somewhat valid concerns given the conversation in this room about having a separate API to configure it with VPP. So we broke that out so that one piece could be upstream, the other piece could be kept, a smaller piece in the sandbox or something. But at the end of the day, they just took it. So that's the only reason they're two separate plugins. It could have been the same thing.
but they can coexist.
Yeah.
You could use LinuxCp without using Linux and and
Yeah.
we know of someone who, I think he programs mostly VPP via the shared memory API, so I think he has route daemons running, but he doesn't use Linux NL for everything. So basically, you've got two separate components. One of them is let something, a program running on the kernel talk, send packets and receive packets through VPP. That's the LinuxCp plugin. And then the other piece of it is Linux NL, and that's kind of allow kernel configuration to propagate into VPP so that you don't have to write a separate application that knows VPP's API to add routes.
I get it now, because generally those FRR, they interact with the kernel.
Yeah.
In order
Right.
for it to basically be populated into VPP, it has to go through the Linux NL. There is no other.
There actually is another path, and it's much harder to manage because you end up maintaining FRR as well. If you dive into the 6 slides, it's discussed a little bit. We had a fork of FRR that communicated via a different path. It's supposedly supported in FRR, but it's harder to use.
Yeah, if you want to use, FRR that you downloaded from GitHub or from some FRR website, I don't know where they distribute packages. If you want to use stock software that you got used on other systems, you're basically using kernel.
It's all
It's code if you want to try and use the other
Yeah.
path. A lot of people, they don't want to do that.
They populate routes in the kernel also. You have routes in the kernel, now you have other routes in VPP.
correct.
So you have basically 2 copies of the routes in the.
And then the interfaces in VPP can also be interfaces in the kernel. FRR sees interfaces it know of. The link speeds match what it expects to see. The admin state matches. The link state matches. It's happy. It's like, okay, I've got interfaces. I've got peers for BGP talking to me. I'm happy. I'm going to insert routes. I'll compute a fib and give it to the kernel. When that happens, it shows up in VPP. Anything else?